Today we're going to talk about the delta function. The delta function we're going to define in terms of what are called impulse functions. An impulse function is a function delta sub k of t, which has a height of 1 over 2k between minus k and k, but is 0 otherwise. You can see a graph of delta sub k of t pictured on the right. How do we interpret that physically? We can think about this as being an impulse that starts at t equals minus k and ends at t equals k. So we're thinking about it as a function that represents some sort of force or some sort of impulse, and it's 0 all of a sudden until t equals minus k, and then it turns on at t equals minus k, and then it turns off again at t equals k. Now we can ask some questions about this type of function, like what is the integral of this function over all of the time? So if we integrate from minus infinity to infinity of delta sub k, we notice that that function is 0 everywhere except for between minus k and k. So we can actually just integrate between minus k and k, at which point the function delta sub k of t is 1 over 2k, a constant, dt. So if we're integrating a constant, that's just the height, 1 over 2k, times the length of the interval, which in this case is 2k. And so that integral is in fact 1. Now we can ask questions like, what happens as k gets smaller? What happens as k goes to 0? Well, let's look at some functions. Let's look at delta sub k over 2, which would start at minus k over 2, and then it would finish at k over 2. Well, that function would actually be twice as tall. Its height would be 1 over k instead of 1 over 2k. And it would go from minus k over 2 to k over 2. So we have a function that's a little bit shorter in terms of when it's not 0, but it's taller. What about from minus k over 4 to k over 4? So if we did delta sub k over 4, well, that's going to be twice as tall as the last one, but the interval is going to be half as wide. So again, we get a narrower interval, but it's going to be a taller function. Okay, so the function, as k goes towards 0, is going to get thinner in terms of when it's not 0, but also taller. And what about the physical interpretation here? Well, the impulse in this case, it's going to get shorter, but the magnitude of that function is getting larger, it's increasing, so it's going to get shorter but stronger. So we can think about it as having a stronger impulse, but for a shorter amount of time. Now, if you look at these rectangles, okay, we had that the area under that rectangle was 1 when we integrated from minus k to k. But again, because this is twice as tall, the integral under that the integral of that rectangle is going to be 1. And then when we got this impulse to be narrower, but it was twice as tall. Okay, the area of that rectangle, or the integral under that function, is again going to be 1. So notice that the integral always stays 1. Okay, so what happens as k goes to 0? Well, we can look at the limit as k goes to 0 of the integral from minus infinity to infinity. of delta sub k of t dt. And we'll notice that that's the limit as k goes to 0 of the integral from minus k to k of delta sub k, which is 1 over 2k dt. But that's the limit as k goes to 0, as we saw before, of 1 over 2k times 2k. So that's the limit as k goes to 0 of 1. So that integral would be 1. So the limiting function still has an integral of 1. Well, we're going to give that limiting function a name. It's the unit impulse function, or delta function. And it's defined by two properties. Now, the first property is that delta of t, okay, which is going to be 0 for t not equal to 0. So if you look back at the plot of this function, delta sub k, if we take the limit as k goes to 0, then the interval on which this delta function is not 0, it shrinks. It shrinks all the way down to the point where delta of t is going to be 0 everywhere except for at t equals 0. So this function is 0 everywhere. But it also has this interesting property that if you integrate from a to b delta of t dt, that you will get 1 if 0 is in the interval from a to b. Okay, so imagine that my delta function is, as k goes to 0, is getting thinner and thinner, as you can see in this diagram, right? But it's getting taller and taller, and it's maintaining an integral of 1. So as long as I integrate somewhere that goes from a negative number to a positive number, then I'm going to capture that tiny, tiny, tiny infinitesimal interval on which the delta function is not 0 and on which its integral is 1. But then, if I don't capture the integral, if my interval does not capture 0, if it doesn't contain 0, then the integral from a to b of delta of t dt is going to equal 0. So if 0 is not in the interval from a to b. So you can imagine that if I integrated on an interval out there or over here, then I'm not going to capture that part where the delta function is not 0, and so the integral is just going to be 0. Okay, and these are the defining properties of the delta function. But you should note that the delta function is not actually a function. This limit, okay, this limit as k goes to 0 of delta sub k of t, it doesn't actually exist, because at that one point, the delta function would have to be infinite. Okay, and we can't define a function to be infinite at a point. So it's actually, the delta function is actually what's called a distribution, but that usually takes a lot of graduate level math to define. So we just need to have some sort of understanding of what we think the delta function is physically, and that is it's an impulse that is as short as possible and as strong as possible at t equals 0. Okay, it's a force that's going to be as for as short a time as possible, and it's going to be as strong as possible at t equals 0. You kind of think about it as being infinite at t equals 0 and 0 everywhere else, and its integral is 1. Now what we can do with the delta function is we can shift it to a specific time at a time t equals c. So what properties will the delta function have if I'm looking at delta of t minus c? Well, delta of t minus c is going to equal 0 everywhere as long as t is not c. If t is c, then I have delta of 0, which we know we can think of as kind of being infinite. And then the delta function has the property that delta of t minus c dt, so the integral of delta of t minus c dt, that's going to equal 1 if c is in the interval from a to b. That way I capture that moment when I have delta of 0, okay? And then it's going to equal 0 if c is not in the interval from a to b. Okay, so this is just a shift of the delta function. Now, because we've been talking about Laplace transforms, a natural question that we can ask is, if we let t be, or c be greater than 0, what is the Laplace transform of delta of t minus c? Okay, so we want to find the Laplace transform of delta of t minus c. Well, that's going to be the integral from 0 to infinity of e to the minus st times delta of t minus c dt. So what I'm going to do is the first thing is I'm going to do a u substitution to kind of shift that integral. So delta, or u is going to equal t minus c, and then du is going to equal, in that case, dt. If I do that, then the integral starts at negative c, because when I plug in t equals 0, u is negative c. It still goes to infinity. And then I'm going to get e to the minus s. And then t becomes u plus c. And then I get delta of u du. Now, I'm going to pull an e to the minus sc out of my integral. And I'm going to be left with the integral from minus c to infinity of e to the minus su delta of u du. But here, I'm going to replace delta of u with its definition, the limit, as k goes to 0 of delta sub k of u du. Now, the reason I'm going to do that is because then I can plug in what the formula is for delta sub k of u. So I'm going to take the limit as k goes to 0 of my integral of e to the minus su, and that's going to be times 1 over 2k du. But now I need to integrate over where the delta function is not 0. Okay, so the delta function is not 0 between minus k and k. And what I need to do is I need to make k small enough, make it less than c, so that I'm just integrating between minus k and k. So here we're going to assume that k is less than c. We can do that because we're taking the limit as k goes to 0, so we can make k as small as we want. Now I just have the integral from minus k to k. All that's left to do is to do that integral. Okay, so we give e to the minus sc. I'm going to have the limit as k goes to 0. I'm going to pull the 1 over 2k out front, and then the integral is minus 1 over s e to the minus su evaluated between minus k and k. So this becomes e to the minus sc. This is the limit as k goes to 0. I'm going to have a minus 1 over k times s times, let's see, we're going to get e to the minus sk minus e to the sk, if I plug in the negative k, and I'm going to put the over 2 over here. And hopefully what you notice is that what's inside this red box, what's inside that box is going to be minus sinh of sk. So you remember our definition of sinh, e to the sk minus e to the minus sk over 2. So this is minus that. Okay, so that's going to give me e to the minus sc times the limit as k goes to 0 of sinh of sk over, in this case, sk. Now, if I took that limit, the top would be 0 and the bottom would be 0. So in order to take that limit, I'm going to apply L'Hopital's rule. So L'Hopital's rule says I need to take the derivative of the top and the bottom. The derivative of sinh is cosh, so this is s times cosh of sk. And then the derivative with respect to k of s times k is just s. So the s's, in fact, cancel, and I'm left with just cosh of sk. I take the limit as k goes to 0, and I get e to the minus sc times cosh of 0. Cosh of 0 is, in fact, 1, if you work it out using the definition of cosh. So we found that the limit, or the Laplace transform of delta of t minus c is equal to e to the minus sc. And that's actually pretty cool, okay? Because what we got a Laplace transform of something that isn't even quite a function because it doesn't exist at a point, okay? But the Laplace transform of that delta function turns out to be something nice and smooth, e to the minus sc. Now, we could repeat this whole process essentially for any function. And if we repeated this process for any function, we would get the following theorem. If f of t is continuous, then the integral from a to b of f of t of delta of t minus c would actually be the function f of c, or the function f evaluated at t equals c. As long as c is in a to b in that interval. If it's not in that interval, then the delta function is 0 everywhere else, and so this integral is just going to be 0. So this is important because the delta function, essentially it collapses integrals. Okay, if you integrate against this impulse that's as strong as possible for as short as possible at a time c, then it just gives you back the value of the function, and it gives you f of c. And that is almost a defining property of the delta function. So be sure to look at this theorem because we'll use this kind of reasoning throughout. Okay, well now I want to start looking at solving differential equations that have delta functions in them. So I want to solve an initial value problem, y double prime plus 4y. So when we see this, we're thinking pure oscillation. Okay, but it has a forcing term. That forcing term is delta of t minus pi over 4. If this was a mass spring problem, it would be saying that at that time, pi over 4, we're going to hit that mass as hard as we can for as short of a time as we can. We're going to hit it really, really hard for a very, very short time, okay, and we're going to see what happens, okay? This mass is stretched to a length of 1/2 and then let go from rest. So let's see if we can solve this problem. So I'm going to take the Laplace transform of both sides. So that's the Laplace transform of y double prime plus 4 times the Laplace transform of y equals the Laplace transform of delta of t minus pi over 4. Okay. So the Laplace transform of the second derivative is s squared y minus s y of 0 minus y prime of 0. And then we have plus 4 times the Laplace transform of y, which is capital Y. And the Laplace transform of that delta function is e to the minus s pi over 4. Now, y of 0 is 1/2. And y prime of 0 is going to be 0. So I can write this as s squared plus 4 times y, and that's going to equal 1/2 s, if I bring that to the other side, plus e to the minus s pi over 4. So y in this case is going to be 1/2 times s over s squared plus 4 plus e to the minus s pi over 4 over s squared plus 4. So I can take the inverse Laplace transform to get little y of t. Little y of t is going to be 1/2 cosine of 2t. Okay, so the inverse Laplace transform of s over s squared plus 4 is cosine of 2t. And then I'm going to treat the s squared plus 4, I'm going to multiply top and bottom by 2 so that I can think about that as being 1/2 times, and then now I'm going to use the e to the minus s pi over 4. When I do the inverse Laplace transform, I'm going to get h of t minus pi over 4, so the heaviside function of t minus pi over 4. And then now I have a 2 over s squared plus 2 squared, so that's a sine. So this is going to be the sine of 2, and not t, but t minus pi over 4. Okay. Now, if that's your solution, that's fine. You can write it that way. I'm going to make one adjustment. This is 1/2 cosine of 2t. And then I'm going to notice that the sine of 2 times t minus pi over 4, okay, that's in fact the sine of 2t minus pi over 2. And essentially, that's a shift of sine by pi over 2, which is actually just cosine of 2t. Okay, well, what does that mean for y of t? You don't have to write your solution this way, but it's helpful for interpretation. Well, you'll notice that essentially I've turned on 1/2 cosine of 2t, and then, brief thing by the way, when I shifted that, that actually becomes a minus cosine of 2t. I apologize. Okay, so I start with 1/2 cosine of 2t, and that's exactly what I get when t is less than pi over 4. But then the other term turns on at pi over 4, and what it does is it subtracts 1/2 cosine of 2t starting at pi over 4. And so in fact, this becomes 0 when t is greater than or equal to pi over 4. So what I have is the start of a cosine curve that all of a sudden stops. Okay, so let's look at what this would look like. So if I have my axis here, and then this is pi over 4, then my cosine starts at 1/2. And then all of a sudden, it goes down to pi over 4, and then it just stops, and it becomes 0 after that. And so that's what my solution y of t looks like. Okay, so it starts as being the normal oscillation, but at t equals pi over 4, we hit it with a force as hard as we can, but for as short of a time as we can, and it actually stops the motion of that spring. It doesn't oscillate anymore. Okay, so that's what the delta function is doing in this case. It's just stopping the motion of that mass spring system. Okay, let's move on and let's do one more example. Okay, we're going to solve an initial value problem, y double prime plus 2y prime plus 5y. Okay, so what we're going to do is we're going to add friction to the system now. Okay, we're going to add friction. Okay, then we're going to hit it with a delta function times sine of t. Okay, that's what we're going to do at pi over 6. So initially there's going to be nothing to this system. There is going to be, it's going to be at rest. Okay, it's going to start at 0. There's going to be no initial velocity. So we're just going to wait until t equals pi over 6. And then we're going to hit that mass as strong as we possibly can for as short a time as we can at pi over 6. And then watch what happens. Okay, so the Laplace transform of y double prime plus 2 times the Laplace transform of y prime plus 5 times the Laplace transform of y, in this case, is going to equal the Laplace transform of delta of t minus pi over 6 times sine of t. Now, again, the Laplace transform of y double prime is s squared capital Y minus sy of 0 minus y prime of 0. Then we're going to get plus 2 times sy for the Laplace transform of y prime minus y of 0. And then plus 5 times the Laplace transform of y, which is capital Y. And then, what is the Laplace transform of the delta function times sine t? Well, it's the Laplace transform of the delta function e to the minus 5 pi over 6. And then the sine t becomes sine of, sorry, not 5, that's an s. E to the minus s pi over 6. And then it becomes sine of pi over 6. So we're essentially using that rule where we integrate the function f of t times the delta function, and we're evaluating at pi over 6. Okay, well, let's plug in some of the initial conditions. 0, 0 derivative, there's another 0. That's just going to make this problem just a little bit easier to solve. So I'm going to get s squared plus 2s plus 5 times y is going to equal, okay, the sine of pi over 6 is a half, so this will be a half e to the minus s pi over 6. So y in this case is going to be 1/2 e to the minus s pi over 6 divided by s squared plus 2s plus 5. Now, what's in the denominator is not something that I can factor, so I will have to complete the square. So I'm going to get s squared plus 2s plus 1 plus 4. That way, the s squared plus 2s plus 1 is a perfect square. So I'm going to get 1/2 e to the minus s pi over 6. Divide that by s plus 1 squared plus 4. Okay. Now we might need to consult our Laplace transform chart in order to figure out what this is. Another way to do it is to realize the s plus 1. If you look at that, when we do the inverse Laplace transform, that's going to be a shift by e to the minus t. Okay, so then what I really have is a 1/2 e to the minus s pi over 6 divided by s squared plus 2 squared. Okay, so I'm going to have to multiply top and bottom by 2, and what I get is going to be 1/4 e to the minus s pi over 6 times 2 over s plus 1 squared plus 2 squared. Okay, so what I have is a sine function, a sine of 2t, as shifted by that e to the minus t. So y of t is going to be 1/4 e to the minus s pi over 6. This is going to give me, just so you know, a heaviside function of t minus pi over 6. Okay, so that's going to be a 1/4 heaviside of t minus pi over 6. Then I'm going to get the e to the minus t that comes from the s plus 1. And then I would have sine of 2t, but I'm not going to have sine of 2t because I'm shifting for that heaviside function, so that's sine of 2t minus pi over 6. So that is going to be y of t. So what I have is a function that does not start until pi over 6, and then it looks like a decaying exponential times sine of 2 times t minus pi over 6. So what I'm going to do is I'm just going to graph this function real quick for you. And that function isn't going to do anything until pi over 6. And then it becomes 1/4 e to the minus t sine of 2 times pi over 6. So that's a shifted sine function. So essentially, it's going to be 0. And then when I graph it, okay, it's going to start a sine function. That's a sine function that's going to decay over time. Okay, so I'm going to try that one more time. So it's going to look something like that. Okay, so I'm going to, at t equals pi over 6, I'm going to knock that mass on a spring as hard as I can for as short of a time as I can. And then what I get is something that starts to oscillate, but because of the friction, that oscillation will be underdamped, and so it'll decay to 0.